The Marine Tech Expo is going virtual this year. Welcome back to Marine Tech Expo 2021 from Plymouth. Coming up in this session, the all-important issue of data protection. With an ever-increasing reliance on autonomous technology, how do we guard against cyber attacks? We'll also look at the work being done to ensure there's confidence in autonomous systems at sea. And just a reminder that at the end of this session, there'll be a chance to put your questions to our guests. Now, wherever you are in the world, the threat from cyber attacks is a constant danger. The battle to thwart them has never been more important. Our next speaker is at the forefront of that battle. Kevin Forshaw is from the University of Plymouth and has been working with ship operators, builders and equipment manufacturers to build resilience against maritime cyber attacks.
I'm Kevin Forshaw. I'm from the University of Plymouth. And I want to talk to you today about our efforts to mitigate cyber attacks on shipping. So maritime cyber attacks have been growing exponentially. This is ports, ships, and now increasingly autonomous vehicles. Port of Barcelona was hit in 2017, Maersk hit by NotPetya in 2018, and CMA were hit by ransomware in October last year. And this latest attack on CMA now means that all four of the big shipping lines have been hit by maritime cyber incidents. This is concerning because 96% of world trade is moved by ship. And COVID, Brexit, and also recent incident in the Suez have highlighted the fragility of these supply chains. A ship provides a very complicated attack surface. So firstly, ships vary tremendously. Many different shapes and sizes, carrying many different types of cargo. Ships also operate for about 25 to 30 years, which means there is often a complex mix of legacy systems with modern bolt-on autonomous additions. The other complexity around ships is around the mix of both information technology and also operational technology in the system that is a ship. So when you think about the network on a ship, it's not simply an IT office-based network. You have many different operational technology additions to that network, rudder control, for example, engine management. And there are also changing maritime threats. So we have moved from piracy, as we would have known it 200 years ago, to now significant harm being possible from one person, one very bright person, with one PC. And we are moving into a world of organized crime where they know that shipping is quite an easy target to hit, and also state-sponsored terrorism. We have GPS spoofing, which is affecting many of the world's shipping lanes, including the Straits of Hormuz. So the Maritime Cyber Threats Research Group at the University of Plymouth is now the largest of its kind anywhere in the world. And it combines our maritime heritage. The University of Plymouth started as the School of Navigation in 1862, with our extensive expertise in networks and security. And bringing these two areas together, we now have quite a large body of people looking at how to mitigate maritime cyber threat. And what I want to talk to you very briefly about this morning is a new laboratory called CyberShip, and also our approaches to dynamic risk assessment, and also another project where we're looking at impacts of maritime cybersecurity in port environments. So the CyberShip Lab is a 3.2 million investment into a hardware-based lab at the university. This lab standing for Software, Hardware, Information and Protection. It is very much hardware-based. It's not simulation. And what we are doing is recreating a ship's bridge at the university. So all the equipment you'd normally find on a ship's bridge, such as voyage data recorders, radar, ECDIS, etc., all configured together, and we can then test that setup, that system of systems, with known malware, custom crafted malware, and the impacts of GPS spoofing and other maritime cyber attacks. It's a collaboration with many different partners. It's funded by Research England, but we have partners including BT, IRM, Eaton, Hensoldt, and Netitude. Many of these companies are providing us with equipment for the laboratory and working with us to configure it. So this is a shot of the equipment vault at the Maritime Cyber Ship Lab, which contains some of the equipment I've already mentioned. Here we see ECDIS, voyage data recorders, and radars. And the equipment in this lab, in the vault, in the lab, is now increasing, with many different suppliers donating different bits of equipment that you would find on different vessels. In the other section of the laboratory is where we start to do the network analysis. So when we have configured all the equipment in the vault to represent a specific ship's bridge layout, we would then start to subject that to known malware. And the screens here will allow us to monitor that network traffic and to see any vulnerabilities in that equipment. We are also starting to look at various OT operational technology aspects, particularly including rudder control. This following some of the work we looked at after the impact of this Suez incident recently, and really demonstrating how easy it is to subject a ship's rudder control system to maritime cyber attack. So that is our Cyber Ship Lab, a very exciting new development and a unique facility globally. And it's much better to recreate a ship's bridge within a laboratory at a university than to actually subject an actual ship to the impacts of maritime cyber attack. So this facility will genuinely increase resilience of the sector as we go forward. In addition to the Maritime Cyber Ship Lab, we've also been looking at maritime cyber risk assessment. This is a presentation of a leading article that was published in a leading maritime journal back in 2019. So MACRA, standing for Maritime Cyber Risk Assessment, uniquely provides dynamic, multi-dimensional risk assessment tooling that addresses both those information technology and the operational technology elements of a specific vessel system. And unpacking that a bit more, what do we mean by dynamic, multi-dimensional risk assessment? Well, a ship is a moving vehicle whose parameters are constantly changing. And what we are doing with MACRA is taking known issues, known vulnerabilities with that ship system, and then cross-referencing those with the threats associated with the cargo being operated, being carried, and the route being operated. And you need to think quite laterally about the cargo as well, because it may be a bulk carrier, maybe a container ship, but equally it's as applicable to a cruise liner where the cargo is a lot of wealthy people, high net individuals who could be subjected to ransomware. It's dynamic because as the ship changes, whether it's a change in the system or whether it's a change in the cargo or the route being operated, this software tooling will recreate a new risk profile. And crucially, what MACRA offers operators is an ability to get a handle on their voyage-specific risk and really start to invest in the best areas to affect resilience against maritime cyber attacks going forward. So that puts MACRA, and I'd now like to move on to a project called CyberMar. CyberMar, funded by European Commission, Horizon 2020 programme. This is a project looking at cyber preparedness actions for a holistic approach and raising awareness in the maritime logistics chain. So it's developing an innovative simulation environment for logistics, combining a knowledge-based platform and decision support tool that will incorporate novel risk analysis and economic metric models. It's a project that involves 13 maritime logistics organisations working with the University of Plymouth. And a question raised there is why ports? Well, obviously, a shipping platform moving into a port, again, it's a wider system. The port environment is connected to the ship platform, and any malware introduced onto the ship system or onto the port system will then migrate to the other system. And as we move to a world of increasingly connected smart ports, where the ports are then connected to terrestrial transport, which could be road and rail going forward, it is easy to see how a maritime cyber incident on a ship can then spread to those terrestrial environments. So just to conclude about what we are trying to do more generally at the Maritime Cyber Threats Research Group at the university. So at the moment, we're in a situation, as I said, where cyber attacks are increasing exponentially, but they're largely going unnoticed, and they're largely being reported as mechanical failures because the shipping operators do not understand that those mechanical failures have been caused by a maritime cyber incident. So what we are trying to do, working with the operators and other maritime stakeholders we're engaged with, is essentially harden systems to tampering. At the same time, we're working on projects looking at voyage data recorders, where we can collect forensic information to start to detect attacks and start to report back on the plethora of instances that are taking place. This data will then allow us to create more effective investigation tools and also artificial intelligence-based intrusion tools. So when we understand the extent of the incidents taking place, we can then get into a situation where we can monitor them and start to assess risk and prioritize their vulnerabilities. Also working with class societies and other organizations, including the International Maritime Organization, IMO, we want to move quickly to a position where we have a compliance or audit suite, where new equipment manufacturers can bring along a piece of new equipment, plug that into the cyber ship lab, where we can run a standard compliance audit suite to assess any vulnerabilities with that piece of equipment. As increasingly IT and OT converge and shipping moves to a future of more autonomous ships with a lot of autonomous systems being bolted to existing ships' IT, OT systems, where we want to get to is to create a holistic understanding of that connected system of systems, and then examine the security across both the hardware and the software and the people, remembering that crew training is often a very effective way of mitigating cyber attacks. And coming back to Marine Tech Expo, as I said, ships, we're moving to a future of autonomous ships. And a lot of our thinking is equally applicable to smaller data collection marine autonomous systems. And as we move to a future of smart ports, looking at how those autonomous ships will engage with smart ports so we can embrace the efficiency of smart ports without compromising security. But also as we move to a future of those smaller data collection autonomous platforms working offshore, it's again looking at that Internet of Things infrastructure in offshore environments and ensuring that all this is cyber secure. And we're very pleased to be working in the wider Plymouth ecosystem. The Cyber Ship Lab I've already mentioned at the university, but also we have cyber ranges. So these are ranges isolated from the main network where malware can be tested for propagation and custom crafted malware can be created. These can then be fed into that cyber ship lab to see how the equipment fares, how individual bits of kit fare, and how the system responds. And when we know that, we can then feed realistic training scenarios into our ship bridge simulator. But also looking more widely at Plymouth, we are increasingly engaging with smart sound. So smart sound is the most heavily instrumented stretch of water, I think, anywhere in Europe, if not the world. And here we can see how autonomous systems transferring data between themselves and looking at a future of autonomous shipping coming into smart ports. And again, it gives us the opportunity at the university to engage with this facility to ensure the cybersecurity of that data being generated. So that gives you a very quick overview of the Maritime Cyber Threats Research Group at the university, our cyber ship lab, and also maritime cyber risk assessment approaches to dynamic risk assessment. Thank you very much for listening. My name is Kevin Forshaw, Director of Industrial and Strategic Partnerships at the University of Plymouth.
Thank you to Kevin Forshaw from the University of Plymouth. Now, you may be aware that 2020 was supposed to be a year of commemoration here in Plymouth, UK, and the city's namesake in America. It was the 400th anniversary of the sailing of the Mayflower, the famous ship that took pilgrims from Britain and Europe to the New World. Well, those commemorations sadly were curtailed by the pandemic, but one of the most exciting initiatives to come out of the anniversary was the development of a Mayflower for the 21st century, the world's first fully sized autonomous ship to cross the Atlantic. To explain more about the project, here's Matthew Ratsey from Marine AI, whose systems were used on board the new Mayflower.
Hi, my name is Matthew Ratsey and I am Managing Director of Marine AI, and I'm joined today by Oliver Thompson, who is our lead software robotics engineer. And we're going to talk to you a little bit about Marine AI and what we do, and also about Mayflower Autonomous Project, which is our technology demonstrator. So Marine AI was founded back in 2017 by Brett Farnath, who is Managing Director of MSubs. Marine AI is a subsidiary of MSubs. The main purpose of Marine AI is to allow some of the autonomous and AI software which has been developed by MSubs over the last 20 years to be deployed in the commercial marine environment. Marine AI is based in Turnchapel Wharf, and since December 2020 we've grown the team and now employ over 13 people, working both in Plymouth in the UK and Toronto in Canada. We have named our AI software Guardian, and today I'd like to talk to you briefly about the products we offer and also about the Mayflower autonomous ship. So our aim as Marine AI is to deliver sensor-driven cognitive, artificial and augmented intelligence to enhance maritime capabilities on and below the water. Our key partners in that are IBM and NVIDIA, and we have called our software Guardian. We have four main products, and they're all building bricks on each other. So we start with what we call Guardian Vision, and that moves through to Guardian Manned, and then Guardian Autonomy and Guardian Port. Guardian Vision is simply object detection and classification. Guardian Manned takes the output from Guardian Vision and couples that with additional sensors such as radar, AIS, GPS, if it's appropriate, LiDAR, navigation, and gives the information to a person on the bridge. There's a human in the loop for them to be able to make a more effective decision about what to do. Guardian Autonomy takes a human out of the loop and allows the vessel to make its own decisions using the same sensor bases which we have in both in manned. Guardian Port is a separate product but allows us to offer all the sensor suite which we have in autonomy, but in a port environment to enhance safety and enhance ship movements. The foundation of Guardian is that it uses scalable at-the-edge sensor analytics for the machine learning, computer vision, and the Colregs rule sets. We have limited bandwidth-friendly actionable information which can be transmitted to land-based teams using low bandwidth solutions such as the Iridium Certus. And this gives us accurate vessel control and safety management. Here are some examples of some of the recent deployments we've made. to demonstrate the technology. This is a simple computer vision system which we installed for some tests in London, and you can see on this middle slide how we're able to put a bounding box around an object and detect it. Exocean have been using our equipment for their survey vessels on their wind farms and survey work. And then we come to the Mayflower autonomous ship, which brings together all the technologies we've been working on and is a technology demonstrator. And I'm going to hand over to Ollie Thompson, who's just going to talk to you a bit about some of the sensor technology and how that's been fused together over the past few months.
Yeah, so as Matt says, this is a combination of two of our main products. So we've got Guardian Vision as a sensor input, and then we fuse that with a number of other sensors such as AIS, radar, and as well the cameras. And that leads into our Guardian Autonomy, which is Guardian manned, but the actions are put in place, and there's a decision engine on top of that, which looks to replace the man in the loop. So what we're really trying to achieve with Mayflower at the moment is getting our kit out there, getting it in a very varying conditions, harsh environments, that sort of thing, so off the coast and in the Atlantic, to be able to really put our software through its paces as well as our sensor fusion. So one of the primary issues with running an autonomous vessel is being able to trust the data you're receiving. So ECDIS, so charts, are never quite as exact as they ought to be. So we're able to fuse that data with other sensors, such as the altimeter, also as well as the vision system to be able to detect boundaries and other vessels as well. In addition to that, being able to follow the rules of the road as well while we're underway. So COLREGS is a framework of rules that allow navigators and people piloting vessels to predict the movement of another vessel so that you can proceed in a safe manner. And we have to abide by that if we're going to navigate into waters autonomously. So being able to really trust the sensor data that you're working on, so being able to know exactly where a vessel is, what its course over ground is, what the speed over ground, etc., is really important. And that's what Mayflower's been able to do for us. So she's been going out in coastal areas, performing trials, and we've been running simulations and getting our own support vessels to become targets and sort of assess the decisions that she makes. And that's been really, really useful, and we wouldn't be where we are today without such a demonstrator. So it's invaluable really to get out there and get real world data. So yeah, she'll continue to do this sort of stuff, take her out into more challenging situations, like I said, the Atlantic, although not as heavily congested and difficult as the coastal areas, we have other challenges like sensors start to degrade in worsening conditions, sea states, etc. So she's a perfect platform for being able to achieve the coastal elements and work with that sort of intensity of contact, as well as being able to go out further because the vessel can perform in those sorts of challenging environments as well.
Thank you, Ollie. Hopefully that's given you an insight to some of the technology which has gone into Mayflower. Just by way of a quick update for those of you who may or may not have been following the news. So Mayflower recently left on her maiden transatlantic voyage, and we had a very good few days to start with, and she was about 250 to 300 miles southwest of the Scillies when we experienced a generator failure. And we had to take the decision on what to do. We decided to bring her back. She made it most of the way back by herself before the generator finally killed itself, and we recovered her, and she's now back in Plymouth, where we will do a refit and assess the situation, and then the plan is for her to go again and make another attempt at the transatlantic in the autumn. Hopefully that's given you insight as to what we are doing at Marine AI, the products which we're offering, and how that technology can be used and is being demonstrated as being used with vessels such as Mayflower. Thank you for your time.
Thank you.
Thank you to Matthew Ratsey from Marine AI. Well, as we've heard, autonomous technology at sea is developing rapidly, but much more work is needed to ensure its reliability and safety. It's crucial that the maritime industry has confidence in the technology to help drive up investment. That's where our next speaker comes in. Burgess is from the National Physical Laboratory, which is helping to establish appropriate measurement infrastructure to support the reliable development, testing and operational assurance of these systems.
Hello. Thank you for inviting me to present on behalf of the National Physical Laboratory. It's a pleasure to be here. My name is Burgess and I work in the Strategy Directorate. The topic today is the assurance of marine autonomous systems. Ensuring confidence in emerging autonomous transport systems, whether these be land, sea or air, will be key to the speed of their exploitation and the delivery of benefits. This presentation provides a brief introduction to MPL's approach to addressing this challenge. So to introduce MPL, we are the UK's National Measurement Institute, and we develop and maintain the national primary measurement standards. So from resilient timing infrastructure to unhackable quantum communications and superfast 5G, technological advances must be built on a foundation of reliable measurement to succeed. Our role in the national measurement system enables governmental and societal requirements to be met across national challenges. As a national laboratory, MPL is currently active with industry and regulatory stakeholder groups across a range of applications of AI, both in how we use AI to support our metrology science and also how our measurement science can be applied to assure confidence in AI itself. One manifestation of our work is in the autonomous transport sector. Now, to be clear, the focus is not just on vehicles and vessels which drive, fly or pilot themselves, but also on remote operation and smart systems which may be enhancing or replacing human situational awareness, and also the overall system of systems such as future UTM. Our focus is supporting the assurance of these systems throughout their development and operational life cycle. And we are focused on addressing the problem that current test and certification approaches are insufficient for assuring these novel emerging systems, and new ones must be developed. Our objective is to develop the appropriate measurement infrastructure to enable this. I mentioned the assurance life cycle. Now, what this means is it is not sufficient to assure a system at one point in time, for example, when it leaves the factory. Rather, assurance is something which begins in design and development and continues all the way through the operation of a system. Now, this is particularly important for systems which may, for example, degrade, or they may receive software updates which may change them in some way, or they may encounter environments they were not tested for example. So, in this slide, with regards to measurement infrastructure, this is a demonstration of how we work collaboratively across stakeholder groups, including, as I said before, government agencies and programs, regulators and standards bodies, test beds, industry and associations, national agencies and PSREs, and academia. And by working on a range of collaborative R&D projects and deploying our capabilities developed through the National Measurement System, to date we have defined the following broad outputs for part of our work. These are highlighted in the grey boxes in the middle, and I'll now talk further about a couple of these, particularly around data confidence and also sensor assurance and virtual testing. So with regards to data confidence, I would like to briefly talk about MPL's work on this and ensuring confidence in the decisions of systems using that data. The world is transforming digitally. Emerging technologies are all around us, and things like the Internet of Things, artificial intelligence, 5G communications, additive manufacturing and distributed ledger technologies will come to define our future. All are enabled by the effective use of data, and the successful adoption of these technologies will depend upon their ability to get data management right. So generating trusted data and providing the confidence needed to take action on the information it provides will be vital for businesses, governments and society in this increasingly digitized world. Now, equally, without the measurement tools to provide confidence in data, it will become harder to reliably quantify the risk associated with decisions which are derived from the same data. This is when things go wrong, sometimes fatally. As we hand over more responsibility to systems where humans are not involved, we need to develop new approaches for assurance to ensure we can trust them, and that includes data standards. So data quality standards are important in the same way uncertainty as a statistical concept is a key component of measurement science and is an important aspect of data quality, and one that is comparatively straightforward to quantify. Establishing proof of trust within the system and the appropriate governance model involves the application of measurement infrastructure and standards throughout the data lifecycle, from sensor input on the left to outputs from decision-making algorithms and everything in between. So there are many factors to consider when measuring the quality and reliability of data to provide the required confidence. A few examples are, and there's not limited to these by the way, so for data quality to be a useful measure, it has to be defined in relation to a specific task or question. High quality data used out of context is actively misleading. Always start by defining what it is that you want to know. Does the data you have cover every risk and sensitivity that you need to assess? This is also linked to data bias. Does the data have the appropriate contextual information associated with it so you can answer the above question? For instance, data collection based on a tick box form may not include all factors you need to consider, but free-form data is difficult to process. Is the data quality time dependent? And if so, is the data you have still relevant? Have you got enough data to answer the question? Is the data traceable back to a standard? Does it have an associated uncertainty statement? Not relevant maybe for some forms of data, but both are vital for anything claiming to be a measurement. And also, has anything been deliberately done to the data between it being gathered and me seeing it? So me might actually be the system that is making decisions. Many sensors have internal algorithms to clean, filter and enhance that data. These are typically written for a specific problem in mind, and their application can introduce bias and increase uncertainty. It may also actually be difficult to test that particular bit of processing. So the better understanding, the greater our confidence can be in the data and decisions from the system, including an AI one. Now I'd very briefly like to touch on some current work, which is an example of our focus on data confidence. This relates to the assurance of the sensors used on autonomous transport and how this links to reliable virtual testing environments. So our interpretation of the challenge is as follows. Unmanned or self-piloting vessels and cars and drones rely upon perception sensors and other data inputs to determine their state and that of their physical environment and the behaviours of other agents around them. This is a critical safety issue. Now there are currently no standardised metrics for measuring sensor performance or the degradation thereof. This also impacts on operating reliable virtual test environments. This is important as you need to test a lot of different scenarios explicitly. And virtual testing using simulated equivalents is quicker and better for rare and dangerous scenarios. The big question we ask is, how can we be confident that performance in the virtual environment reflects performance in reality? And a further question is, how can we make the process cost effective? In addressing this, MPL takes a probabilistic and evidence-based approach. So for the last 14 months, for example, MPL and the Met Office have been collaborating on a project sponsored through the Centre for Connected and Autonomous Vehicles to provide the concept of and create a specification for a usable and reliable framework for characterising sensor performance in different weather-related conditions. This also includes the ability to assess performance outside the design envelope. We're now moving into the testbed development stage, so we'll actually be getting some proper reference data, and beginning to work also with marine stakeholders to explore how we migrate this framework for use by that sector. The underlying principle of this framework, which is designed to support the validation of safety assurance and simulation testing of AV, is as follows. Better confidence in sensor performance can be achieved by a series of linked tests, so each of these ovals is a different test environment, and the characterization exercises at different levels where sensors and full systems are tested both in reality and virtually. It's important to understand that because weather demonstrates significant small-scale variability and sensor response has associated uncertainties, the uncertainty calculation is critical and must be reflected appropriately in the virtual simulation. So in this case for CAV, and there'll be a variation of this for marine, you have your calibration test, you have your external weather test bed, you have the control environment test bed. As you can see, the outputs of these tests are fed into different model elements of the virtual test environment, denoted by the pink circle. These tests supply sufficient confidence in the sensors and sensor models, which is vital for reliable virtual testing of the autonomous system, because virtual testing must reflect the likely variability of the sensor responses. This, in turn, helps address the question of virtual testing, reliability and affordability. So now I've only briefly scratched the surface of both the challenge and what we're doing to help address it. And I'm very happy to discuss further offline with any of you. In the meantime, thank you very much for listening.
Thank you to Andre, to Kevin and Matthew, all of whom join us now live to answer your questions. And don't forget, you can submit those questions in the comments box of the YouTube channel. Thank you, all three of you, for joining us. Kevin, I just wanted to start with you, first of all, because your presentation raised key questions regarding the security, the cyber security of our shipping. For instance, you mentioned the Suez incident recently in the last few months, which lots of people will be familiar with. What did that tell you about the vulnerability of shipping?
Okay, so I think the first thing to say with the Suez incident, it wasn't, as far as we were aware, caused by a cyber attack. But what we've shown in the laboratory at the university is it's incredibly easy to actually tamper with the rudder control system. So should you be minded to do so, you can sort of guess the rest. So in terms of, key shipping channels such as the Suez, in terms of key port facilities around the country, if you can take control of the rudder system, of the propulsion system of a ship, which you could then cause quite a major incident, and that's then going to block up the whole of the sort of Western world's economy for a very long time. So yes, incredibly serious, and surprising that more attention hasn't been given to the whole issue of maritime cyber security.
Indeed, and I guess that the issue of the vulnerability was the fact that it had real-world consequences, and we're still feeling the effects of that in terms of delays in delivery of materials from around the world. That's had an impact on costs, an impact on the economy, which is why cyber security is so crucial. And you talked in your presentation about it growing and growing. Tell us where those threats are coming from, if indeed you know where those threats are coming from.
So the threats at the moment, I mean, we do have sort of state-sponsored terrorism. This is Russia and Iran, particularly around sort of Straits of Hormuz. We've seen the GPS spoofing, GNSS spoofing. So this has become a sort of state-sponsored tactic. But I think more concerningly is this organised crime and the potential for organised crime. Most of the cyber incidents that have taken place on the major shipping lines have been ransomware incidents. And of course, if you are a very large floating platform a long way away from land and your systems start to malfunction, you don't really have an awful lot of choice in terms of paying that ransom or not. And this is unfortunately what we've seen so far, that a lot of the shipping operators affected are then paying the ransomware. There have been several operators who've been sort of subjected to ransomware three or four times. And I think what we're trying to do at the university is to bring this shipping community together, because if we can get the operators talking together, talking about how it affected their operations, that's going to give us greater insight so that we can roll out more effective mitigation measures to the entire sort of world shipping fleet.
Can you give us some examples of cyber attacks? If ransoms haven't been paid, have there been attacks that have brought ships to a halt or affected navigational equipment? Have there been real-world examples of cyber attacks that have had consequences?
I think the problem we're also having as well is what can be reported in a responsible way. So what we pick up in terms of journal publications is possibly not the whole truth. It's more the sort of conversations we're having with operators. So to date, with the ransomware instance, it's affected instrumentation. The potential threat is there to completely disable the ship. That hasn't been enacted yet, but as far as we're aware, it is perfectly possible to do so. So like I say, as we look to a future where we hope there is no further incident, that is good. But as organised crime realises how vulnerable shipping is, I think that's unlikely. And I think we rapidly need to move towards a future where these systems are safeguarded, particularly around the key sort of propulsion and navigation systems. So yeah, I don't know if that's answered your question. Not happened yet. The threat is there, and as far as we're aware, it is all completely possible.
And we will come on to the work that you and colleagues and others in the sector are doing to try to mitigate or indeed eliminate altogether some of those risks. We'll come back to you in a moment, Kevin. Matthew, I just wanted to bring you in. You gave us a little bit of an update on Mayflower in your presentation. Just let us know what more you've learned, first of all, from her first few days at sea. What did you learn about the equipment and the capabilities of the ship before the subsequent problems that you encountered? What were you getting from it?
Thank you. Yes, well, in fact, the trip was actually very, very successful. And, you know, from an AI point of view and an operational point of view, we were really pleased with what we achieved in the first 4 or 5 days. What actually failed was a small part on the generator on the exhaust, which unfortunately ended up being catastrophic because if the connection to the exhaust on the generator fails, ultimately you end up filling the boat with generator fumes, which obviously means that eventually the generator chokes, all our hybrid power generation goes down, and we're only able to generate enough solar power, which really on this side of the Atlantic only gives us about 40% of the house load on a daily basis, so not really enough to carry on. So is we could have limped on, but we made the decision that given that it was fairly early days and we'd really quite like to keep the vessel, and she was still only sort of 250 miles southwest of Scilly, to bring her back. So where we are now is that the boat's back in Plymouth. She's out of the water, and we're undertaking basically like a big clean because the internal on the boat is just covered in exhaust fumes, i.e. soot. So we're stripping out all the sensitive electronics and cleaning them up. The generator's obviously out the boat, and you know that is either going to be replaced with a new generator or at least a new engine with a different exhaust system, should I say. But yeah, no, we were really pleased with the operational side. We had an operational command center in the room behind me here, and what we were able to view with the computer vision and the coal regs avoidance systems on the boat, you know, was we were really very pleased with.
And of course, this gives you an opportunity, I guess, to assess the data that you got in those first few days, to tweak and make adjustments now before perhaps another attempt in the autumn. Sure. What are the key things you will be sort of focusing on from the AI point of view that you can sort of develop further in these few months you've now got an opportunity to look at things again?
Sure. I mean, well, there's nothing fundamental. It's just lots of little tweaks. I mean, everyone always says you learn more from failure than you do from success, and I think that's always the truth. And you know, we've got you know, I won't bore you. We've got a whiteboard full of little tweaks we want to do. I mean, the work never stops. You know, we're always trying to improve. But you know, fundamentally, what we set out to do works. Yeah, we've got a host of things we're going to just tweak and change. You know, from the computer vision side to the integration with the radar and the AIS and the way we digest the information and, you know, all the rest of it. I mean, you know, there's a huge amount of detailed stuff we'll end up doing, but fundamentally, the core product which we put out there, you know, really performed well, and we're very pleased with it. And
it's a tremendous landmark commemoration for Mayflower, but presumably a lot more will emerge from this. How will what you are developing for Mayflower expand into the wider real world? What sort of applications could it have beyond what you're doing with Mayflower?
For us, it already is. I mean, you know, we are a commercial organisation, and you know, we've been doing, and as I think everyone probably knows, we're a spin-off from MSubs. So we have that database, if you like, of AI models and information from the years of their defence work. But just as Marine AI, we were doing proof of concept work at the back end of last year, which has transpired into commercial contracts this year, and we've got you know, a handful of other commercial work, you know, significant commercial projects, which we are engaged or very close to contract signing on for the next year. So I mean, it is happening now, and what we've done with Mayflower is fully transferable, and we will be using the learnings from that for delivering the commercial projects which we've been tasked with.
Andre, let me bring you in at this point. What we've heard so far today and in the last few presentations in particular raises lots of questions about how robust and resilient these systems will be and how we go about testing those systems to make sure that they are robust, that people have confidence in them. But I'm interested in a couple of questions have come in about this. What sort of impact will all of this technology, do you think, have on the rules of the sea, how people interact? Because there are very clear lines of shipping movements in many of our busy waters now. How will things change as autonomy becomes more commonplace?
Oh, that's a very good question. I think I can give you some thoughts on that one. Certainly, one of the challenges is how AI systems individually are developed, and the principles. I noticed that Matthew referred to colregs. The question is, are all AI systems equally developed with colregs in mind, or some other approach such as I must avoid collisions and I have a methodology of reward or some other system for arriving at how I avoid collisions? I think that's one of the challenges, particularly though when you've got this interaction between human piloted vessels and ones that are autonomously piloted, and then potentially others which are remotely operated. Are we going to see different behavioural patterns and how do they interact? So I think that's one of the problems. Certainly, work we've done in, not so much in aviation, but certainly on the land-based side, that's a significant challenge as well. And my understanding from talking to various marine experts in this is that they envisage a challenge as well in how some of these vessels will interact with a more human piloted system. I think the other bit also that I come back to, and in fact, hearing Matthew, I see one of these big challenges is how do you do the ongoing operational assurance of these systems? And actually, people think it's all about, can you continuously trust the AI decision making, or even the sensor performance? But also, there's other systems on the ship that can go wrong, or the vessel that can go wrong as well, as Matthew pointed out, which have nothing to do with that. I mean, they're highly linked and highly important to the system. And it's understanding how do you maintain that operational assurance at all times. You might not even know there's a problem with the system initially, somewhere else on the vessel, but it's actually impacting the overall performance.
The variables are almost unimaginable, aren't they? I mean, there are so many factors at play: climate, weather, other shipping movements, as you've pointed out. How do you sort of accommodate all the variables that a ship at sea might encounter?
Again, I think this answer will evolve over many years, by the way, because I think we're still at the beginning of the learning on this. I think one very important thing that I've observed is the importance of linking the limits of your operation to how you design your system. So the sensor suites, the software design, etc., the capability of the actual vessel, and linking that to how it operates and its operational limits, I think is very, very important. Rather than trying to say, I've got a system that will just do everything and go everywhere, I don't think that's practical. It might become practical in the future, but will it ever be necessary? I don't know. And other people will answer that through developing the right business cases. But I think that's a sort of starting point. I think the other thing also, yes, there is a huge amount of variability and complexity. One of the things I alluded to in the presentation is the work we're doing is trying to find a way to take on that complexity and reduce it down to something which is more usable, whether you're testing or assuring or developing. And that's why we bring in ideas of uncertainty characterization and other things, which potentially make this a lot easier to work with.
Matthew, if I could bring you back in at this point, because Andre made a very good point there. The AI is great if it's interacting with other AI, but when you bring in the human factors as well, a human is trying to second guess what the AI might be doing. How have you factored in the AI on board Mayflower and its interaction with human-controlled shipping?
Well, yeah, it's a very relevant, interesting point. I mean, I can give you a good example. I mean, it's maybe quite difficult to describe without a diagram here, but we had early on in the voyage, we had quite an interesting colreg scenario where we had a vessel overtaking Mayflower and two vessels coming towards her. Now, what everyone should have done from a colreg's point of view is that the boat behind should have turned to starboard, and the two boats coming towards us should have turned to starboard as well, so we'd have gone port to port. In fact, what happened was the boat behind did turn to starboard correctly. The boat ahead of us decided she wasn't going to move at all. and the other boat moved to starboard as well. We ended up going through the middle, but we had no choice. But that is an example in the real world. Just because the colregs are there, just because they're human controlled, doesn't mean that they're actually going to get the decision right the whole time. And actually, most of the time, they I don't know what the percentage is, but they're not getting decisions right the whole time. So that's a challenge. With the AI side, we can make it follow a set of rules, but if the humans aren't following the rules, then that makes it hard as well.
Yeah, I mean, it's the same as talking about the autonomous vehicles on our roads, that it's fine if that car knows the rules of the road and is following a straight line and driving along okay. It just takes some human behind the wheel of another car to veer into its path, and then there could be problems. And same factoring that in at sea, I guess.
For sure. I mean, luckily at sea, generally things are happening a lot slower, and the density is a lot less. I mean, you only have to go online and look at some of the stuff, the work that Tesla's doing, and so you can see that the challenges we face at sea are not quite in the same ballpark as what they're facing on the road, which is why small companies like ourselves are able to get up to speed with the work we've done and operate.
And Kevin, bringing you back in, because listening to Matthew there and to Andre and some of the issues of managing AI, again, that's where cybersecurity plays a big part in this, because if cybersecurity breaks down, these systems could be easily manipulated.
Yeah, that's very true. And I think, as one of the presenters said this morning, one of the introductory sessions, we're going to see a massive increase in all things sort of ocean economy, which means we're going to see a much greater volume of vessels of all different types. And, if we look at the sort of floating wind opportunity locally, they reckon that's going to require construction of 2,000 additional specialist support vessels. And those human piloted vessels are going to be used in conjunction with a load of unmanned vessels, which are there to go and collect data for the sort of operational maintenance inspection. So we're going to see a much larger increase of traffic, some completely human piloted, some semi-autonomous, but increasingly getting, more and more autonomous, more and more sophisticated as we go forward. And then a larger number of vessels that are going to be completely autonomous. And because we're going to have this greater congestion in that ocean space, which at the moment, as Matthew rightly points out, it's not congested yet, but it will be increasingly congested. Any breakdown in an artificial intelligence element of that wider sort of marine traffic system can then impact on the human piloted system. So yeah, it is a concern. And of course, the other issue that sort of some people are not aware of, as we move to fully autonomous shipping, they're going to be satellite connected. So you're then going to have packets of data going from satellite to a large number of vessels. So it potentially is not going to be one vessel that's impacted. It's going to be a large number of vessels that could potentially be impacted at the same time.
And that's where Cyber Ship Lab that you described comes in to help sort of understand what these threats are and how to mitigate them. Take us through how that lab works. How will you process information and data and work out where the threats are coming from, and indeed how to avoid those threats, to eliminate them altogether?
Okay, so normally on a ship's bridge, you have about 30 different pieces of standard equipment. You've got radar, you've got ECDIS, you've got voyage data recorders, etc., etc. So what we're doing in the lab is we're assembling all different types of sort of makes of all that key equipment you'd find on ships' bridges. When an operator comes to us to say, can you determine the resilience of my specific vessel, we can then configure all the different bits of kit that you would find on that particular type of vessel. We can then subject all that kit, which is then one overall connected system, to the effects of malware. So that can be known malware that we know already exists out there. We can then custom craft malware to predict what organized crime could do in the future. We can then subject that entire system of systems to that malware or GPS spoofing, GNS spoofing. We can then see how the entire system responds to that. And we can also see which individual bits of kit start to fail and how they fail. And when we have that greater insight into how maritime cybersecurity can impact a specific operation, we can then get into more effective mitigation. So that could be making equipment more resilient, so redesigning the equipment so it doesn't fail. But it could be, other aspects such as crew training. When we know exactly what's going to happen to a vessel, we can then play out that maritime cyber attack in our ship's bridge simulator so that crews can effectively learn to spot the signs, and then they can go through effective processes to actually mitigate the impact.
And coming back to you, Matthew, in terms of Mayflower, clearly you were using a lot of data transfer, messaging, sensors on board Mayflower, sending information back to you. obviously you can't go into all the security arrangements you put in place, but how big a factor was that in constructing Mayflower systems?
Yeah, it's certainly a factor, but I mean, we believe we're mitigating at a simplistic level. We're mitigating it by using edge devices, which certainly helps. So you know, that and using sort of industry standard best practice allows us to have reasonable surety that what we're doing, you know, and we certainly had no instances, touch wood, where anyone was trying to hack the boat or anything like that.
And in terms of where we go with autonomous systems, Andre, let me bring you back in at this point. I mean, if there's still a great deal of work to be done in terms of bringing assurance levels up and really getting confidence levels up in these systems. Do you see a time when it is possible to have purely autonomous vessels, or will autonomy just be an element of a vessel that will still be crewed?
I think that's, again, it's a very good question. I would say that I do see a future with full autonomy, but it will be slightly a sort of horses for courses type approach. And I think that it's about how the business cases evolve and also how other demographic and other social factors come in. You know, if fully autonomous vessels can be proven to, for example, drive agendas around things like net zero, that's great. And that will drive that business case. At the moment, certainly the work we're doing, the discussions we're having, I'm very much more focused on sort of systems where humans are less involved or not involved at all on a vessel, but vessels usually still crewed, but not always. Smaller vessels which might have some degree of remote operation, and also some vessels which do go off and do their own things autonomously, and they have a good use case for doing that, a good business case for doing that. I don't envisage a future where everything is autonomous, put it that way. I think there'll always be definitely crewed ships out there. But again, I think it'll be for industry and the people who use these things to decide that in the future.
A question that's come in for everyone on the panel to comment on, but I'll start with you, Andre, if you wouldn't mind. This is, could the panel comment on how to have assurance in so-called non-deterministic software?
Well, firstly, not just in terms of the software itself. I mean, I think it's very important to have sort of software validation capabilities, and really, I think you've got to look at this at the very top level of how we potentially regulate AI going forward more generally, rather than just look at it just in terms of marine. One of sort of the mantras that we have at MPL is standards and regulation are very important, but they shouldn't present a massive barrier to innovation. So I think when it comes to software development, you have to look at the whole system as well. You've got to look at what other elements there are in there which meet or match up with the software design itself. That's about as far as I'm going to answer that one, I think, at this point. Okay. Otherwise, it gets a bit too detailed and complex.
One other question for you, Andre, before we move back to other members of the panel. Are you looking at other environments, land and air, AI, autonomy, application and regulation, to learn lessons and exploit coherent approaches?
Yeah, and that builds on what I was just saying. I mean, we actually work at the governmental level looking at overall regulation of AI, and then we look at transport, one of those key areas we're focusing on, because there's considerable safety and other factors that come into this. I appreciate in marine, perhaps the safety focus is less so than, say, with land or air. But also the focus is different in air, because there you're looking at system of systems. But what we've established, and this is in working in conjunction with other sort of key national agencies and organisations, is there are certain activities and certain, if you like, certain aspects of assurance which are common, or certain underpinning frameworks to that assurance which are common. There are other things which will be unique, and I think that's where you have to start from, because that hopefully simplifies the whole process. What we're trying to avoid is making it over siloed and over complex, because then obviously that stifles innovation in this country as well.
Matthew, bringing you back to Mayflower for a moment, a question here. Can Mayflower classify aid to navigation like different buoys or lights in order to strengthen its understanding of its surroundings?
Yes, can it detect buoys? Yes, is the answer. Yeah.
And in terms of the future, I mean, you've given us an outline of where Mayflower's project is going. Longer term, the things you're developing with Mayflower, where do you see those systems developing further, and in what way will they be applied?
Well, I mean, it's the whole maritime space, and I think probably what we'll see is just an increase in the amount of autonomy and AI being used, with a sort of a more human in the loop scenario. I think going to the full autonomy is going to take a while for the reason Andre's already highlighted, to do with regulation. But I think you'll see an increased accelerated need for the AI side to be implemented in marine vessels.
And in terms, Kevin, of cyber security going forward, the future of that, it was concerning, I guess, to hear at the start you say that perhaps it's not been taken as seriously by many people as it should be. How do you now bring that up the agenda? How do you sort of make sure that the industry is buying into this? And for instance, you said in your presentation, it's often reported as a mechanical issue rather than something that was perhaps a cyber threat. And maybe we don't even know the full scale of cyber yet. So how do we ensure that that's known by the wider audience and talked about more openly?
Yeah, it is a tricky one. I mean, I think we do have a place for sort of those shocking sort of scare stories, which, you know, we have ourselves used in the past. And I mean, you know, if we look at the UK, for example, if you were to shut down 3 of the major port facilities, you could bring the country to its knees within 3 working days, because we are so wholly reliant on maritime transport for everything we use in this country. You know, it's not just food, it's not just clothing, it's the fuel oil to drive our power stations. And if we haven't got all our power stations functioning, we then haven't got drinking water, we then haven't got sewage, etc., etc. So we're crucially reliant on maritime. Shocking scare stories have their place, but, you know, I think what we also need to be mindful of is not to give too many people out there ideas of what could be possible. So we have to approach this in a very measured way. And what we're doing at the university is, like I say, engaging with a large number of shipping operators, a large number of other maritime stakeholders who are producing the equipment, insurers who obviously ensure the safe transport, regulators who are bringing in all the appropriate regulations to mitigate it. And I think it's approaching them in a measured way, bringing that community together so that we can openly talk about the issues and what is realistically possible now, and then collectively forge those solutions as we go forward.
Okay, we're out of time on this question and answer, but Kevin Forshaw, Matthew Ratsey, Andre Burgess, thank you, all 3 of you, for joining us live at Marine Tech Expo 2021. And that's all from this session, but we'll be back after this short break when, amongst other things, we'll be looking at how autonomous technology can help marine science. That's coming up in 15 minutes.